Hello and welcome to this deep tech interview with onsemi for Mauser. I'm your host Stuart Cording, the electronics reporter. If I were to mention robots in the context of industrial automation, you're probably thinking of robot arms welding car chassis and installing windscreens. In these examples, the robot arm is bolted to the ground and fenced off for safety, while the workpiece is brought to the robot. But in today's world of increasing efficiency and optimization of menial tasks, we're seeing a growth in untethered robots that operate alongside humans and move to wherever the workpiece is located. Although such autonomous mobile robots, known as AMRs, vary significantly in design, they share many common characteristics. These include their own power source, a wide array of sensors, connectivity and, increasingly, some level of intelligence to tackle the unexpected autonomously. To get the lowdown on the latest technologies that are making AMRs possible, I've invited Theo Kersjes, Global Application Manager at onsemi, and Aly Barakat, Technical Marketing Engineer at Mauser, to share their insights.
Hello, Stuart.
Hello, a pleasure to be here.
Well, it's great to have you both. And Theo, I'd like to start by asking you the first question, which is to expand on that definition of AMRs I've just given, perhaps sharing what you and your applications team are seeing at the customers you support.
Yeah, currently today it's a very broad group of different types of robots, and I have here a slide with some definition and characterization of each of those. We might use that quickly to go over the slew of different robots. And as you mentioned, on the left side on this slide, there's the autonomous of the big robot that was used in industrial applications, which was fenced off. Next to that, there was the automated guided vehicle, the AGV. This had a line on the ground, and it could follow that line, and it would stop if there's an obstacle, but it cannot go around the obstacle. So these AGVs are very clear to people if you're working in the same space, what they're doing and how they're behaving. And that's one characteristic that we need to keep in mind when we go to the newer systems. Secondly, or the thirdly, then the autonomous mobile robot you see here, the warehouse robot that got that name that we're now using for this whole category, where Amazon currently operates more than 1 million of these robots in their warehouses. And these first three initially were all programmed with traditional software methodologies, and slowly we got some machine learning, AI, and other techniques in there that were required to even control more motors more dynamically. And that's why the cobalt, which is the next category, got its popularity. The 6-motor arms. Now it's getting hard to control all these motors to go to a certain physical position in space. And that is also uses now waypoints. So you can set waypoints by moving the end effector or the thing that's attached to this arm to do something to different locations, and then the robot will automatically fill in the path and or considering safety, keep out areas and other things. That's where I met Aly doing the cobalt activities. We did that onsemi. We have a lot of motor drive, motor control for these systems, power solutions, AC/DC compute. And we had a demo at a trade show, and Aly came over and he said, "That's cool. I want that to look at that as well." So that's where we started our cooperation about, I think it was 3 or 4 years ago.
Wow.
Yes.
That's how it starts, isn't it? And I know Aly as well, and I can understand his interest in such an application. I would have done exactly the same if I'd been in his position. Now, Theo, would you say then that there's sort of a standard architecture for AMRs emerging, sort of comparable to the standardization we've seen in PCs? Or do AMR designers tend to sort of optimize the architecture to the task and the deployment location?
Yeah, so definitely there is commonalities. So after this cobalt, now you see a standardized platform emerge. You see an arm on a mobile base, which we call an autonomous mobile manipulator. And then from that, then the humanoids come as well. And these all are battery operated. They all have battery charging capabilities. Then they need certain sensors to be able to do their path planning and driving safely around people, because we now want to use these more flexibly outside of their warehouse, maybe even as a delivery robot in our own neighborhoods or on agricultural settings in fields where sunlight might be effect, or shadows, hard shadows, where sensors can be overloaded. So yeah, there's a commonality between them. If you split them up in power levels, you can even say there's a lot of commonality with the power solutions as well. Of course, if you go higher power solutions, you come into the EV type of silicon carbide solutions for traction inverters, which onsemi also has. But with these robots, it tends to stay below 4 kilowatt. Let's say that, so a golf cart size apparatus that does something.
Fantastic. Now, one of the things I mentioned at the beginning is that those industrial robots that we've typically seen in sort of marketing films, they're bolted to the floor, they're in a safety cage. And the whole purpose of that is also to avoid injury to humans operating in the vicinity. But these AMRs, not only do they need to sense their environment to ensure safety, they also need some sort of spatial awareness as well. Are designers relying purely on one type of sensor, like a camera comes to mind, or are they combining the inputs from multiple sensors to do that?
Yeah, some designers have a whole philosophy around this and like to use one type of cameras, or in most cases a camera sensor. But that's not really cost efficient. The compute needed for an spatial image segmentation or something you want to do in an image camera is way more than using, for instance, an ultrasonic sensor. And other techniques like an ultrasonic sensor are very good at detecting glass objects or objects that are hard to detect with an image sensor. So if you would have a full sheet of glass or some other obstacle mirrors, you can think of, if you have robots that operate in spaces where humans are, you have these fancy mirrors in spherical shaped in to look around the corner. And a drone with only an image camera might have a hard time and thinks it can fly out the mirror, or doesn't know that it's around the corner. Whereas the ultrasonic sensor immediately detects this as a solid object. Um,
Yeah.
so it must be something else. So definitely ultrasonic, but also LiDAR and other technologies, other sensor modalities.
Now, I've taken a look at various image sensors over the years, and I'll be perfectly honest and say I'm still a bit unclear on what impact features like the rolling shutter and global shutter have. So what are the requirements AMR developers have of image sensors, and how do they then go on to determine which optics match with that sensor?
Yeah, definitely for spatial awareness, you need some kind of depth sensing, and onsemi just launched our latest ITOF, indirect time of flight depth sensor, which is a image sensor, 1.2 megapixel high resolution, that from the camera immediately provides a depth field that then can be used to make this spatial awareness in some navigation applications. In general, you cannot solve everything with one type of image sensor to create one type of camera. And you can think of some of the pixels that you create in the image sensor might be more light sensitive to light or to color, and that might be helpful in certain situations. And so we created our Hyperlux series of different cameras. Some are very fast, and so if you have a stereoscopic application where your robot looks into its surroundings and wants to do a depth field with stereo cameras, you need very fast responding cameras because of the fast moving objects around the robot. In other cases, You can use very high resolution cameras for detecting some specific application it's doing. So we have these categories, and these categories are then identified by some key characteristics, like, for instance, high dynamic range, where you might think when you drive in a tunnel and you all of a sudden come outside, the light might blind you for a second. So we have cameras that can fix that and just look out of these scenarios and still see clearly what's happening, so the robot can determine what to do. And this is also what you need in with industrial robots when they go into shadowy areas or come into agricultural field applications or stuff like that.
That's great. There's one of those big challenges that you see is even with the phone cameras, for example, that challenge with big differences in light, and it's incredible to see how that's then solved at the semiconductor level. Now, power is obviously another key challenge in AMRs, to get the most out of the batteries first of all. And then you've also got the charging and the power conversion to an efficient motor drive. What demands are being placed on your team with regard to that part of the application?
Interestingly, the owners of these robots have the same problems as EV owners. They had some range anxiety on the batteries. Does my robot is it able to complete its whole mission during the shift time or the run time I want to have out of it? And there's different ways of solving that. Of course, higher efficiency of all the components is always a drive to that. And I'll come to that in a minute further. But another thing for warehouse robots, where you have many of one type of robot, you can add some robots if it doesn't fit your profile, and then charge them. You can do intermittent charging or opportunity charging, where they quickly charge if they have nothing to do between jobs. And we see already some humanoid robots that exchange their own battery packs, which looks really nice. But that implies on a chip level that you have something like a hot swap or e-fuses, where you can protect that process and handle it. And there again, we have many products that can assist with these kind of applications. Lastly, I mentioned I would say something about performance. So motors are in humanoids. There's about 30 motors. So they're very, one of the most complex systems, and they're also very different in humanoids. And for each of those, you might have slightly different power solutions to control them. It's all BLDC most of the time, but you might want to have a higher efficiency to reduce the heat and to reduce the demand for cooling aluminum or cooling plates, so you can make the system lighter.
Super. Well, that's a great overview of the basics of the AMR application and all the elements that come together to make them. Ali, I'm going to come to you now. Now, for those who had the opportunity to visit Embedded World in Germany this year, they'll recall quite a large AMR robot roaming the Mauser stand. Now, that was constructed by you and your team. Can you tell us a little bit more about the project, what its aims were, and the AMR that resulted?
Yeah, absolutely. So the idea behind the AMR project was really to show what the next generation of factory automation might look like. So where robots aren't just like following fixed routes, but actually understand and adapt to their surroundings. So together with Theo and the whole onsemi team, and as well as Mauser continues expanding its industrial automation portfolio, we wanted to build something that connects the components we distribute to real working applications. So we developed this large human-safe AMR equipped with multiple sensors such as 2D LiDAR for mapping and obstacle detection, stereo vision for depth and odometry, mono cameras for object recognition, and lastly, ultrasonic sensors for close range safety. And then this all supported by encoders and an IMU. So at Embedded World, we set up a live demo where a cobot placed a box on the AMR, which then navigated through obstacles to a precise drop-off point. And the goal really here was to highlight how intelligent, sensor-rich AMRs can enable safer and more flexible intralogistics in warehouses and factories. And to show as well that Mauser's technology portfolio is already powering the shifts toward smart autonomous factories.
Now, as mentioned by Theo earlier, AMRs can't solely rely on a single type of sensor or vision system. So instead, they use a system called sensor fusion, which combines input from multiple sensors to improve decision making over a potential single sensor approach. Can you tell us a bit more about how sensor fusion works, and how does it figure out which sensor is the most reliable to make the decision that needs to be made next?
Yep. No, that's actually a great question, and that's really at the heart of autonomous mobility in general. So AMRs essentially it works on probabilities. So nothing is ever perfectly known. So the most important things are perception and localization. The robot then constantly needs to estimate where it is and what's around it, even with noisy or incomplete data. And that's where then sensor fusion comes in. It combines then all those different inputs to build one consistent, more reliable understanding of the world it's in. So now there's a lot of like sensor fusion techniques, but the most like common used technique in autonomous mobile robotics is based on Kalman filtering. So essentially, the robot predicts its motion from encoders and IMU, and then it corrects that prediction using data, for example, from the lidar, camera, ultrasonics, and so on. So the filter's job is like basically to automatically decide which sensor to trust more depending on the situation it is. So let's say, for example, the visual odometry becomes unreliable due to motion blur or lighting changes in a warehouse or factory. Here, then the lidar comes and takes the lead. So in the AMR that we built, we use an extended Kalman filter, which literally like handles the non-linear typical behavior that mobile robotics face. So lidar gives precise geometry. Vision then adds like depth on some context, like object recognition. Encoders keep short-term tracking stable, and ultrasonics lastly ensure like close range safety. So by fusing all of these together, the robot then reduces uncertainty, localizes more accurately, and can navigate then smoothly in dynamic environments where humans are in. And that's really then what makes the sensor fusion like the backbone of any modern autonomous mobile robotics.
Fantastic. Well, thanks for that insight onto sensor fusion. That's made it a lot clearer for me. Finally, one last question for you, Theo. We've covered and touched on some of the silicon devices which are used and required to make a functional and reliable AMR without that will operate as long as required in a factory or in a logistics center. What else is needed, and what requirements are impacting the choices made by engineers?
Okay, yeah, we talk now about the Chat GPT moment for robots. So when become robots so refined in their tasks and behaviors that they can be applied to many different applications. It opens up different use cases. And for that, of course, we need the better algorithms. So there's a lot of happening in the algorithm space and in the way we train these robots. So simulation environments and accelerated training in the simulation space. And this can is currently focused a lot on the behavior or functions of the robot, but you can bring this down to even the chip level where you look at performance of or a battery, how long the battery lasts. And so that's for us the angle of using at these simulation spaces. So that's the algorithm. The next thing you need is better mechanical solutions. And there's some very interesting gearboxes for motors. One is the Archimedes drive, which is basically gears that have no teeth, and they work like a train where the train wheels are smooth on the train tracks, and so you don't have any backlash in these solutions. So there's very different advancements made in the algorithms and in the mechanical solutions. And then of course you need sorry, better different chip integration solutions. And for that, onsemi announced about a year ago, we have the Trio hardware development platform, which is our foundation for our next generation power management and sensor interfaces, as well as communication chips. And this Trio platform is a bipolar CMOS DMOS 65 nanometer technology where we can very quickly use proven IP blocks to create different functionality in the chips that is needed, and this then supports fast time to market, which is then needed for these robotic systems where proven functions that are in an algorithm can be placed in the hardware and used in our products.
Great. Well, thanks. It sounds like an exciting next step, and I think it reflects as well the way the semiconductor industry sort of integrates further as applications take shape, and we understand the challenges involved in a particular domain in more detail. So, thank you for that. Now, as we always do on these little videos that we record for Mauser, we reach out to our community to ask them if they've got any questions on these topics, and luckily, I've got a few notes here. Now, the first one is actually came up while I was talking to some people at Embedded World, funnily enough. And the question was about how this project started. Theo, you mentioned already at the beginning a little bit about what happened and how Aly took an interest in the first demonstrator that you had. Can you give us a bit more background as to what happened next and how you've been working together?
Yeah, so one of the first applications onsemi worked on was a fruit sorting algorithm using our image sensors to detect if fruit is fresh and then bin it in different on a conveyor belt using a robotic arm. And that's what we demonstrated. Aly saw that and he said, can we do something where we would have a water dispensary system where it gives a drink to people. And we created that, and it was a lot of fun. It was one of the first with a little time crunch at the trade show, doing some waypoint adjustments. And then also some integration with the water dispenser unit, which had an inductive button instead of physical buttons. So we had to put something on the robotic finger to make that work. And then they just took it. Aly took it, and they made several different things like ice. I remember give soft ice. They were giving that out and adding conveyor belts, and just put their whole own spin on it. And we went further on the mobile robot then. So yeah, so that's where we engaged, and he is adding challenges to add more sensors and look at different conditions for the sensors in the system. And you could think of like automotive, we have ultrasonic sensors that are under the car, and in robotics, they can be used for that as well to see if there's anything under the robot before it drives away. So many different things that we look at. So that's really nice.
And Aly, both you and me visit regularly different trade fairs across the country, and we see lots of different demos. Some of them are most incredible. But what was it about the AMR demo that you saw from onsemi that made you think, yeah, I need to talk to Theo about that? That's something that we could build upon and do more with.
Yeah, well, first of all, the collaboration, as Theo mentioned, how we first met and how we collaborate together with this water dispenser robotic arm demo. Uh, we had a really good connection from the beginning. So like we enjoyed the time together building it and staying as well after hours in the trade show, trying to figure out everything and make it work seamlessly. So yeah, we just visited their booth and we saw the AMRs. And first of all, it really looked amazing. Aesthetically, it looked really nice. The car was built fantastically, and I said, okay, let's build this. We want to build this as well in our one to have at the Mauser office. So that's where it's kicked off. We began then building one together, making it more advanced, adding more sensors to have it more reliable. And yeah, we then said, okay, this will be our biggest collaboration because it was really interesting to build the car from scratch, 3D printing everything, making the wiring harness from scratch. Everything is like handmade and so on. So it as well a really good experience for like our Mauser team as well to begin diving into this world of autonomous mobile robotics and as well as we're transitioning more and having more of the industrial automation components in our stock that we have hands-on experience with them.
So, Theo, another question that's come up here on my community questions is about AI and edge AI. How are you seeing developers integrating this into their products?
Yeah, so today you see, I mentioned already physical AI, that's the next of level after agentic AI to have robot spatial awareness in the physical world. So then when a robot does a task at a table and something drops off the table, it will know it's out of its visual range. It cannot see it anymore, but if it would drive around, it might encounter it on the ground. So those kind of aspects where we naturally think about as humans, that's now something that's getting into these models for these robots, and they call that physical AI. When they learn that, then you have again a lot of different use cases that you can add and service with robots. And for that as well, we have some hearing aids products, and we see now some use cases where the hearing aids can be put on the robot in its head, where you have it kind of the center of the sensors. So you have your vision system, your hearing system, and then the robot can use these audio DSPs to do noise cancellation in very loud or environments, as well as directional hearing if it looks to you, or it can detect that the speech coming from a certain person and do something with that. And so that is the way then that enables the robot to instruct the robot what to do with audio, with text. And so that's the prompt engineering of the robot, as you say. So we don't have to type anymore. We can just talk to them and engage with them very as we would with other people around us. And it would give again another level of use cases and enablement for these type of systems.
Wow, that's really exciting, and it's interesting to speak to engineers who are out working closely with customers to understand what's being discussed at that cutting edge of decision making around new products. I've got another question here on my list for you, Theo, as well. What are the most unusual use cases for AMRs that you've seen so far?
Yeah, for me, they tend to be around solving some really clever problem. And one of the things I saw was a robot that sits on the hull of a ship. It's magnetically attached, and it would clean the hull of the ship, like almost your vacuum cleaner at home, the little Roomba thing, driving around on the hull of the ship. But it could do that even during travel. So for going into port, it could do that, and they were even now looking at sanding that the paint off, so they could have the ship very short time in dock to repaint. So time it just right that it arrives with the robot being done on the hull, and do these kind of applications. So that was one. A second one is of course humanoid robots. I was 2 weeks ago in a large trade show on robotics, and it was really cool to see. Before, we see now every week these robots, humanoid robots, do fancy dance, but there they actually had 6 or 7 of them sitting on a conveyor belt and working together, creating some products. So that was the first time I saw that. And with that also the hands of the robot. So we called it the hand effector. So they're more human-like hands, and all the new things they can do with these hands is also very interesting. This is really cutting edge. Before or till now, robots are doing pick and place, so they can you order something at Amazon or somewhere, they can go in the warehouse, get the product, put it in a box, and ship it. That was the most complicated task for them. And now it's doing anything where there's abrasive behavior, so polishing or sanding. That's very challenging, and people look at use cases to do that for robot hands. So that those are some of the advancements that are going on.
That's amazing. And I saw another video from Scheffler, which was a similar humanoid robot where they were working alongside humans, but to carry crates from one location to a conveyor belt. And it does very much seem like the humanoid robot is going to be an increasingly important part of factory automation. Now, I've got one more question from the community that came up, and I think this is probably for you, Ali. So the question is about operating systems. Now, we've got operating systems which are quite complex, like Windows and Linux, and right through to very basic stuff that runs bare metal, like FreeRTOS. But the question is that they've heard about a robot operating system, which is known as ROS. Do you know any more about that and how it compares to the operating systems that many of us know?
Yep. So the robot operating system, in short, ROS, makes robotics much more easier in general, like robotics implementation, because there you have packages, specific packages that you can just use and then combine them together to have your specific application met. So ROS here operates in nodes and topics, like in a system called nodes and topics. And what happens is each node calls a specific topic, and this topic calls another node, and so on. So in the end, you have like a workflow of what you want to do with action, states, input, outputs, and so on. So in the end, it makes everything much easier. Now, ROS here is based on Python and C++. So you have parts where you can program it using via Python, and parts you can program via C++. So it makes it as well much more easier for people to either program it in this way or that way.
That's great. Well, thanks ever so much. That's the end of our community questions and also the end of our interview. Thanks, Theo, Ali, so much for your time and sharing your insights with us.
Thank you, Stuart. Thank you, Ali.
Thank you so much. It was a pleasure. Thank you, Theo. See you soon.
Well, that's all we have time for, so let's review what we've discussed. Robots are no longer bolted to the floor inside safety cages. Instead, they are increasingly mobile, interacting closely with humans, and are becoming intelligent too, capable of handling non-uniform loads and adapting to the environment around them. As an engineering task, the development of AMRs is exceptionally exciting, requiring expertise across a broad range of electronic systems. This ranges from power distribution and motor drive systems to wired communication, battery charging, lighting, processing, and sensor fusion. onsemi can be found supporting each of these challenges with products such as the highly integrated mixed-signal Treo platform and their Hyperlux image sensors and time-of-flight sensors. The recent joint project between onsemi and Mouser on their AMR demonstrator also highlights another factor critical to a project's success: collaboration. Only when engineers work together is it possible to overcome the technical challenges that arise during the development of such a complex system. My thanks go to Theo Kersjes of onsemi and Aly Barakat from Mouser for sharing their technical expertise around the topic of autonomous mobile robots. If you're keen to learn about power-efficient motor control, lighting, or the highly integrated sensing technologies that are used in these applications, follow the link to the Mouser website.